I see that we have 92 participants, which is pretty good for the day. So welcome everybody to this session on the future altimetry of the cryosphere. My name's Chris Rapley. I'm Professor of Climate Science, University College London. I'm also Chair of the European Science Foundation's European Space Sciences Committee, and one of the roles of that committee is to act where appropriate as the voice of the community. So if at the end of this session the voice of the community needs to be projected in the direction of ESA or the EC or USPA, the new space agency, we'd be very happy to help. Just very quickly, I've got a long-standing interest in this particular field. I led the original 1982 study commissioned by ESA called A Study of Radar Altimetry over Ice-Covered Surfaces, and that was UCL MSSL, Scott Polar Research Institute, CNRS Groupe de Recherche de Géodésie Spatiale, EG&G, who are the contractors who work for the GSFC team, Jace Wally and so on, and Rutherford Lab. And I've heard a lot of mentions about how surprising everybody's found the fact that the ice sheets and sea ice are very mobile. But actually, maybe the Ipcc didn't reflect this, but those of us around in the early 80s were well aware of what might happen. We didn't know what would happen. And I just note that the first paper on ice sheet altimetry, as far as I remember, was the 1978 Ron Brooks, Bill Campbell, Aaron A. Ramsey, Ray Stanley, and Jace Wally GEOS 3 study of the lower bit of Greenland. That was in Nature. And of course, the first person to suggest using altimeters on satellites was Gordon Robin, and he published a paper on that in 1966. So the only other thing I'd say was that in 1982, the carbon dioxide content of the atmosphere was 340 degrees, so 340 parts per million. So those were the good old days. Thinking back to that, the launch of VRS-1 was a decade ahead of that study. The millennium was 20 years ahead. We're now 40 years ahead. So in this session, we've already heard quite a bit about what's going to be happening over the next 5 or 10 years. But what we're really thinking about is where's that going, and where is the long-term direction of altimetry? So if we can peer through the mists a little, that would be great. So let me introduce my co-host, Mark, who's just got a couple of comments about the session. Over to you, Mark.
Yes, we have 4 esteemed speakers, after which we'd like to trigger a discussion. And we have a number of seed questions that I'll put up after Andy's talk. And I'd like to try and circulate those in the meantime, maybe by Twitter, so that you can already start thinking about them. In the meantime, we've asked the speakers to talk to very specific themes, and hopefully this will enable us to trigger the general discussion afterwards. We hope to have a discussion of around 40 minutes after each of the successive keynote speakers. So please don't go away after the talks. We'd like to engage with you, the user community, in making sure we have some consolidated recommendations as how ESA can proceed in the future. Thank you very much, Chris.
Okay, thanks very much, Mark. And for those of you who don't know, Mark, of course, is head of ESA's Earth and Mission Science Division. So we've got 4 great speakers. Each has got 15 minutes. I'll give a 1-minute warning. We'll take questions at the end of the 1-hour session. So if you can be accumulating questions in the chat box in the meantime, that'll help us frame that first part of the discussion. And I'll give each speaker a 1-minute warning. So it's my great pleasure, first of all, to introduce Valerie Masson del Motte. I'm sure many of you know Valerie really well. She's Research Director of the French Alternative Energies and Atomic Energy Commission, but she's been since 2015 chair of IPCC, or co-chair of IPCC Working Group 1. She was coordinating lead author of the Paleoclimate chapter in AR5 and is currently leading IPCC's Working Group 1 activities for AR6. And Valerie's talk is entitled The Cryosphere in a Changing Climate, What Shall We Be Focusing On? Over to you, Valerie. And
thank you very much. Can you hear me?
Yes, we can.
And can you see my slides?
Yes, we can.
Perfect. So I was asked to talk about the cryosphere in a changing climate and a few highlights from the IPCC 6th assessment cycle. So I'm going to have an emphasis on advances and gaps reflected in the last 3 special reports on global warming of 1.5 degrees Celsius in 2018, on climate change and land in 2019, and of course on the ocean and cryosphere in 2019 too. And I will finish this presentation by an emphasis on the structure of the Working Group 1 report, which we are currently finalizing, with a highlight on the structure and a few advances that I would like to share with you. First of all, in the special report on 1.5 degrees Celsius, there were 2 aspects where I think there have been important advances. The first one is in the context of a widespread retreat of the cryosphere as a direct response to the Earth's energy imbalance, the ability to assess the implications of each fraction of global warming, and especially the difference between a 1.5 and a 2-degree warmer world compared to 1850-1900. One example is related to the probability of a sea ice-free Arctic Ocean during summer, where there's a clear signal of further shrinking for each additional warming fraction. And this report also flags the reversibility of Arctic sea ice loss if there is a temperature overshoot, so the lack of irreversibility. And this is supported by major advances through improved observational data sets and improved modeling. However, the report also highlights key uncertainties related to sea level rise. Whatever happens in terms of greenhouse gas emissions and levels of warming, including limiting global warming to low levels, sea level rise will continue. And this report flags major uncertainty related to ice sheet instability in Antarctica that could imply multi-meter rise of sea level over hundreds to thousands of years, and the lack of an ability to constrain potential thresholds associated with these potentially irreversible changes, and therefore the inability to discriminate between 1.5 or 2 degrees of global warming for these matters. And each chapter of the report flags what is robust, what is emergent, but also gaps or research needs. And one key aspect is the fate of the Arctic permafrost and the implications in terms of carbon release to the atmosphere, and the implications for the remaining carbon budgets to limit warming at levels very close to today. There is a constraint for the permafrost carbon feedback to represent an amount of around 100 gigatons CO2 by 2100, but obviously the uncertainty increases for larger levels of warming and longer time scales. The other aspect, as stressed before, is the deep uncertainty associated with Antarctic ice sheet dynamics, thresholds for instability, and contributions to global mean sea level rise. The report also flags the lack of understanding of the causes for regional variations and recent variations in Antarctic sea ice, and the lack of confidence of Antarctic sea ice projections for low levels of global warming. If we look at the permafrost aspects, both in the SROC and the land reports, they flag that the Arctic permafrost contains about twice the amount of carbon stored in the surface as there is currently in the atmosphere. There is, of course, warming and thawing. Projected thawing is expected to concern a quarter of the current area of permafrost for 2 degrees of global warming, and for high levels of warming like 4 degrees, almost 75% of the near surface area. This is expected to increase the loss of soil carbon, but with low confidence associated to the potential compensation in part due to vegetation growth in these areas. So this is a major source of uncertainty in terms of large-scale feedbacks, but also in terms of local needs for information for local communities to prepare and manage associated hazards. Regarding sea level projections, the report builds on improved understanding of the loss of mass from glaciers from the Greenland and Antarctic ice sheets. It flags the acceleration of sea level rise driven by the increased ice loss from the polar ice sheets. However, it also stresses that in some areas, there has been acceleration of ice flow and retreat. It could be the onset of an irreversible ice sheet instability, but at the moment, there is a lack of knowledge related to the detection of such onset, and this is constrained by the available observations, the available understanding of processes and their representation in models, not just ice sheet models, but also the interplays between the atmosphere, the polar ocean, sea ice, and the ice sheet. At the end of the century, sea level uncertainty is driven by the response of the ice sheets, especially in Antarctica, and in that report we flag and introduce the notion of deep uncertainty associated with permafrost aspects and Antarctic ice sheet aspects. We also flag the remaining inability at that time to discriminate between low level of warming scenarios regarding long-term sea level change, and sea level change beyond 2100 is associated with low confidence. We also flag the importance of low probability but potential high impact eventualities, and this is driven by user needs for those managing critical infrastructure or taking important decisions regarding coastal planning. Low probability but potentially high impact scenarios associated with ice sheet instabilities are important to be considered for risk management over the full scale of risk. This report flags a number of research needs related to the cryosphere. There are key needs in high mountains where observations are constrained by sparse in situ networks and challenges for remote sensing due to steep slopes and cloudiness. But there's a need for progress regarding the distribution and characteristics of permafrost, glacier ice, lake and river ice, and snow cover. For polar sea ice, there's a need to be able to monitor snow depth on sea ice that is critical. As I have flagged previously, there are a number of issues regarding science advances that are needed for polar ice sheets, ice sheet instability, methods to detect the onset of irreversible change from observational evidence. And finally, there's a need for improved monitoring of trends in snow expressed in water equivalent over Arctic land. And this is important for a number of implications regarding the role of snow above permafrost, but also regarding hydrological cycle aspects. I'm now moving to the main Working Group 1 report, which is currently being finalized. We are in the process of collecting government review comments on the draft summary for policymakers. The approval session is scheduled to start on July 26 and the report to be released, if the online approval is successful, by August 9. And this report is designed with a chapter on the framing and a holistic approach, where we first focus on large-scale climate change with the changing state of the climate system in the long-term perspective, the role of human influence on the climate system, and then near-term predictions and long-term projections. There's a strong emphasis on process understanding, with an emphasis on the Earth's energy budget and advances in constraining equilibrium climate sensitivity. There's again a chapter on the ocean, cryosphere, and sea level change, with advances regarding the closure of the sea level budget, as well as new methodologies to be able to provide sea level projections that are consistent with the assessed global climate sensitivity. And the report places an emphasis on regional climate information, looking at extreme events, but also looking at the spread of climate information, which is important for risk assessment. This includes a focus on what we call climate impact drivers, trends, extremes, values above known tolerance thresholds that are currently driving impacts, and they include cryosphere aspects for polar regions or for high mountain regions. We also place an emphasis on storylines of low likelihood but potentially high risk eventualities. This also includes the uncertain fate or response of the Antarctic ice sheet. And I want to flag the major importance of this issue. That chapter on the ocean, cryosphere and sea level is the one that has received most review comments during the 2 phases of review comments, with altogether 75,000 review comments for the whole report, which is based on 14,000 peer review publications. I would like to flag that the draft summary for policymakers is focused on the following storyline: the current state of climate, the range of geophysical possible climate futures from a core set of scenarios and the assessed response of the climate system, an emphasis on climate information that is relevant for risk assessment and regional adaptation, and the geophysical constraints on limiting climate change. And this will feed a synthesis report, which will build on the 3 special reports and the other working group reports, which also assess response options. And that synthesis report will include current status and trends, long-term climate and development futures, and then the possibility and opportunities of near-term responses in a changing climate. So I hope I have given a sense of advances and gaps, and also I have triggered your curiosity for the wealth of information that is covered in the Working Group 1 report that will be soon released.
Valerie, thank you so much for an excellent exposition. We are agog, really, waiting for this to emerge. I'm sure there are lots of questions, but what we have chosen to do is take all the 4 presentations together and then have the questions at the end of that part of this session, if we may. So thank you so much for a really terrific talk, and thank you also for keeping meticulously to time.
Just one word, I forgot to say it. I
Yes.
would like to thank all those of you who have been involved in timely publications to inform the assessment, and all those of you who have been involved in the review process as well. This is critical for the novelty and the quality of the assessment.
Terrific. Thank you very much indeed. Let's move on then to Angelika Humbert, who I'm sure you all know, glaciologist and head of the working group on ice sheet modeling at ARVI, Helmholtz Center for Polar and Marine Research, who is going to give a talk entitled "On the Vulnerability of Antarctica Under an Evolving Climate." Please proceed.
Yeah, thank you very much. And thank you for the invitation to give a presentation here. Yes, I was asked to talk about the vulnerability of Antarctica under an evolving climate. And the setting is perfect because Valerie has introduced so many aspects of making sure they understand the future of the ice sheet. And also on Monday it was, I think, Sophie gave a fantastic talk leading us into that. So what are these key questions? I'm half a remote sensor person and half a modeler. And from the modeling aspect, one of the most interesting questions at the moment is, will East Antarctica gaining enough mass to kind of balancing out the mass loss that we observe and will probably happen in the West Antarctic ice sheet? Then you have a long list of questions that you may ask concerning the vulnerability of the ice sheet with respect to many different areas in the ice sheet. And of course, the elephant in the room is, will the West Antarctic ice sheet become unstable? Now, I think in terms of looking at vulnerability, you may take 2 approaches. One approach is you take an ice sheet model, see it for a moment as a black box. It is a state-of-the-art ice sheet model and a suite of ice sheet models, as we did in ISMIP 6. And then you throw in a kind of boundary conditions, whatever you know about how the climate will evolve in future, and you get the output and you check, what does this output tell you? Another way of doing it is looking at process understanding. and in particular, what you can gain on the processes by combining satellite remote sensing, field observation, airborne remote sensing, and also process modeling. And process modeling is often giving you more information of what would you expect in the future climate to happen than you may be able to represent in a large-scale ice sheet model. So now let's start with the large-scale applications. You have seen that already from Sophie before. In the Ipcc protocol, we were trying as a community to simulate the evolution of the Antarctic ice sheet until 2100. It was really a major effort. And what came out, so here you see on the left-hand side how the surface mass balance is changing, on the right-hand side how the ocean is changing, and it is 6 different kind of global circulation models. You see it looks very different. And if you look at the results that we got, obviously we have a large spread and what the ice sheet models would say how the climate evolves in Antarctica. But one thing is very surprising. You see that there are things where we would say Antarctica is gaining mass, and in other scenarios it's losing mass. But it is not easy to understand what will happen in future in this climate scenario if you look at the different areas. You see that in West Antarctica, tendentially you are losing more mass, but you may gain some in East Antarctica. So from a sea level perspective, you may think you end up fine. But this is a kind of really a weakness in all that, because we know a priori that many of these processes are not very well presented. In addition, there's one drawback of all what we do here. If we want to have a benchmark experiments, we need to think in the way that all community members can contribute, and we prescribe 4 things. And what has been done here is that a group of scientists were taking ocean models and deriving parameterizations for the basal melt rates. Because we think that, as we discussed already in many different talks, that reducing the ice shelf thickness is leading to a reduced buttressing, and this will foster acceleration and with that mass loss. Now, if you look at this distribution here that was published last year, you can get from remote sensing data a very good coverage of the basal melt rates. The question is, how good are these basal melt rates if we derive parameterizations from them that feed into all models? So if you are doing something wrong here, then you may affect all types of simulations that you are doing. If you look into this type of data set in the area of Filchner ice shelf, where we conducted in situ basal melt rate observation campaign, and I just pick out one line that's crossing here, you see there are differences between the in situ basal melt rates that is given here in dots and this remote sensing data set. Given that this is based on different types of satellite remote sensing data sets, you can think in 2 ways of it. Well, there is quite a difference in it, but given that this is such an enormous effort, it is surprisingly little difference in some aspect. In particular, the weakness of this data set is not the ice thickness change observation, that is in this case by CryoSat. It is the coverage for the velocity data set, which is giving you the component of the strain. So think of it in terms of if we can improve our velocity data sets, in particular south of 80 degrees, in that case, this type of approach will be by far better. And with that, inevitably, we will have better forcing for ice sheet modeling and for producing projections for the Ipcc report. But you could also go a bit further and think, yes, it's simple. Ice shelf thickness reduction is leading to buttressing. But what actually does happen in the system? So what really is this method that is taking place there? In some respect, it is very important to think about how will sliding of the glaciers evolve. And sliding means what is the velocity at the base of the glacier. And now if you look on the right side here, you see a little movie that is showing you the change in the basal velocity. And what's the most interesting thing on this movie is how far inland it reaches, not the magnitude for a moment. This is simulated under a scenario which is dumping a lot of additional snow due to warming climate onto Antarctica, and still you have a change in the basal velocity. Now let's dive a little bit deeper into it. The basal velocity of the ice sheet is in that respect the crucial factor, as in the areas where we are close to the grounding line, we are nearly in a plug flow regime, meaning that this basal velocity here is governing the discharge of the ice sheet. So whenever you get something wrong about the sliding velocity, you are wrong with your projections. You are underestimating a process. Now, in addition, if you look at it, if you think of it in one side, you have a stress, a shear stress at the ice base, and then this vast amount of ice that is sitting on top, it is a lubricated gravity-driven flow, and you have friction at the base, and this friction is governed also by the thickness of the ice. So it is the overburden pressure or the weight of the ice sheet that's important here, but you have a little amount of water underneath. And you have heard this morning a lot of talks about the subglacial lakes, which were super interesting. And the water pressure between the ice and the base, this is governing, together with the ice thickness, how fast the ice moves across the base, and with that, how much discharge we have into the ocean. So now imagine you are changing the ice thickness here. With that, inevitably, you are changing the velocity. Yeah, so this is something that we all need to keep in mind. It is a change in ice thickness that is also guiding into a change in the velocity of the glacier. So if you look at this, and in terms of the subglacial hydrological system, of course, the water routing changes with changes in the topography of the glacier. That's well known for a long time. It is nothing new. It's called water piracy, and this has also happened in the area of the Kemp ice stream, where the neighboring ice streams has drawn away water, and the Kemp ice stream has frozen to ground again, and now this is the reason where the ice sheet surface elevation is increasing. So water piracy can lead to both decreased sliding as well as increased sliding, and then you have the feedback. Increased sliding means acceleration, means thinning, and that's in both ways. Also thinning, because it's just an effect directly onto the basal velocity, is also leading to thinning again. So you have a lot of positive feedbacks, and this is why this whole system is very sensitive to the changes in the subglacial hydrological system. Now, if you look at the system a bit into detail, then you may have this distributed systems that were also used this morning by Anna to show you where you have the lakes and so on. But also you can have this channelized system. And most important is, how does that system look like at the grounding line? Because there you have these large changes. So the subglacial hydrological system is in that area governed by the tidal displacement. Now, this is not a climate factor, but still it is connected to the subglacial hydrological system. And with moving tides up and down, you have a change in the water pressure. And you can simulate this if you take such a channelized system approach. And this is a movie that you can see here. You have here the distance to the grounding line, and it changes here the change in this effective normal pressure, and this black line shows you how that goes up and down with the tides. And what you see here, it lasts here up to, let's say, 35 kilometers away from the grounding line. In other areas around the Cyprus coast, for example, this effect of the tides is going up to 80 kilometers upstream. So it is a change that is indicated by the ocean. It's not a climate factor, but a natural factor. But it is kind of acting together with a change in ice thickness elevation due to, in Greenland, surface mass balance impacted by melting, or in Antarctica by acceleration and thinning. So think of it as the climate-driven factor and thinning is interacting with a natural system that is anyway in contact with the ocean and changes over that time scale. And I think there is a lot to learn from forcing subglacial hydrological models of higher order with channels and so by the CryoSat elevation change, and investigate how much that is affecting actually this signal in the acceleration. However, this all would lead to a transient evolution, so not an abrupt change, not a change that you would call an instability. So now let's think about what would an instability look like. In general, it is dramatically different from a transient evolution. And it doesn't matter for that respect if it is climate-driven or internal-driven, but the timescale of instabilities is extremely short. And short in glaciological scales is everything that is below a timescale of years. Yeah, so if you look back to the disintegration events that you have seen on ice surface or floating tongues in Greenland, this always happened on very, very short timescales. You had a change from one day to the next. Within just weeks, you have lost larger parts of floating tongues. So this is always fast. Why is it fast? That's clear. The nature of ice is a viscoelastic nature, and the cracks that are at the end leading to this disintegration are that of a brittle material. And it is calving in a natural system as well with this brittle material. In that case, like you see on the right side here, you have cracks evolving over a long time scale in an episodic manner. But what is most important here, how and why and exactly the route, how you are preconditioning the system for this last change, which is then absolutely fast. So this is something we have to keep in mind in looking into the vulnerability. One thing is the vulnerability of the ice sheet in itself to climate change. The other one is the vulnerability of our society to abrupt changes. So in that respect, I think it is clever to think about what would we need to have a really good and useful evaluation of the health state of the ice sheet, so to say. So imagine we have a suite of different satellite missions. Then you can produce a lot of different types of quantities from these satellite missions. And some of those may lead directly to an information on the health state, like the mass loss from CryoSat, for example. Other satellite products may go into modeling, in that respect, an inverse modeling, as we call it. And then we could learn more from these types of products that are coming out there. And both of them would kind of give us the health state of the ice sheet. And this then at the end would lead us to be able to say it is now unstable or it is approaching an instability. But still we need to keep in mind that instabilities in such type of systems are not easy and clearly defined. So it is also a challenge for the scientists to come up with good criteria to assess it. So I come to my conclusion. I think it is absolutely critical to have a monitoring system of ice sheets in place for the future development of ice sheets. However well we can project things, we will have a large uncertainty. And it is absolutely important to monitor that. And I would want to emphasize no gaps. From the scientist perspective, we cannot afford any gaps. I also want to highlight, do not underestimate the timescale of instabilities and do not miss to monitor the precursors. And I think this is very important to assess the health state. Looking back on now more than 20 years in glaciology, and I started in a theoretical working group with the head of the group who hated to work with data. Satellite observations are providing essential information to build system understanding, and in particular, if you combine it with process modeling and other types of observations. We've learned that in the past, and I think besides having operational systems, all that data is leading us to improve the understanding of the processes. And this brings me to the last point. I think it's very important to have a very close contact between people doing remote sensing and modelers, and not only those who are doing field densification models, but people who think of many different types of processes. Thank you.
Angelika, thank you. Thank you so much for an excellent presentation. Much there to discuss, I'm sure. And thank you also for keeping to time. We will press straight on and come to questions to you later on. So it's my pleasure now to introduce Laurent Valerie. Laurent is the Altimeter product line manager at Thales Alenia Space. Has been involved throughout the successful European development of altimeter instrumentation on board Jason, Altica, Cyrils, the FOSAT, and so on. So his talk will be future directions in satellite altimetry of the Cryosphere. Over to you, Laurent.
Thank you very much. Can you hear me okay?
Yes, and we can see your slides.
Okay, perfect. So thank you very much for the invitation. It's really a pleasure and an honor to be there and to share the past and the future with you. I would like, of course, to acknowledge all my colleagues at ESA and science team, and of course within Thales that have been supported all the work for many years and the future work. So just very quickly, because I do realize we will talk about future, but a bit of background on what is now CryoSat. And just to mention that the story started many years ago, more than 10 years ago. I was just coming back from ECMWF, working on satellite data assimilation, and my colleagues had the good idea to win a contract with ESA. And the name was High Spatial Resolution Radar Altimeter for ocean and ice possibly. And I was very pleased because the story was quite complex, and we started this interesting study, and you see some of the key actors there involved in the study with Duncan and Constantin in ESA. And to make it short, in '99, we proposed the CryoSat mission to the first Earth Explorer, and it was selected, and we were all happy. So we did a bit of homework, and in 2005, we come with the launch of CryoSat, and we know the story. It was a failure. We were all very sad, and ESA very quickly decided to restart with the CryoSat 2 that we know together. But already this was 10 years past, so it's a long story. So in the meantime, while we were reconstructing the #2 CryoSat, I started to be interested in SAR altimetry retracking, in particular for the ocean, because so far discussing with Duncan and others, they say, well, don't bother about retracking. Okay, that could be nice for the application on ice at the time, but for the ocean, we anticipated that we need an accurate retracking. So we look into that in particular using what we call now the numerical retracking. And this was tested when we launched CryoSat 2 on the data. So it was not just a theory, but we started to retrack on the ocean. The first echo looks great. We had an exchange with Duncan saying, well, it looks like theory. It looks almost perfect. And then, you know, the story from CryoSat design at the beginning for ice, it became a success story as well for the ocean. And this led to the Sentinel-3 and to the most recent Jason CS Poseidon 4 altimeter, and in the future, now the Crystal and Iris altimeter. So moving with the future, so Cyril really with CryoSat was really a breakthrough altimetry in many respects. Of course, now it's everybody is used to the unfocused SAR, to the interferometric modes, but at the time this was quite a breakthrough. We were not sure it was going to work at the very beginning, so we are very pleased to see the first echo. ICE mission objectives were met, and we have seen a really splendid presentation today, but as well it opened research and operational application for many other thematics, the ocean, the coastal altimetry, the slope and use imaging mode we have been seeing in detail with presentation by Noël Commandin, the bathymetry, the cross-track ocean shop, hydrology with a fully focused SAR mode. So, and I forget some of the others. As well, we did realize that for the ocean, we got a much better spectrum of the sea surface than we were getting with classical altimeters. So on the top of that, with crystal, now we will make a big improvement for the altimeter called IRIS. Addition of K-band to estimate the snow load on sea ice, and this is crucial for the sea ice. 500 megahertz bandwidth for the K-band. This is big improvement over the KU. Extended DM, I've seen that there is a need for that for ice slope imaging. Digital pulse compression, which is better to have a stable impulse response within the range window, and as well, which is good for interferometry. It's much simpler than DRAMP. If you look into the processing, those familiar with the processing will check that. And we will improve technology with more power, which means a better signal to noise ratio in KU and K-band with new technology in gallium nitride SSPA. As well, we introduce a fully focused mode, which has already been tested on CryoSat, but it was ambiguous, and you can see the plot on the right with the first paper from Rodrigo. Then the SAR interferometric mode as well will be improved thanks to the DEM, and we will get operational data over the ocean with the addition of a radiometer on the satellite for the tropospheric corrections. Is IRIS a safe candidate for HPCM? Yes, indeed it is, because in terms of measurement physics, it is demonstrated. There will be the addition of the K-band. We have already data from AltiKA on the K-band. So now it's a question of meshing both bands for the retriever. But in terms of technology, to secure the development, we have started pre-developments with ESA. In the radio frequency part, this is around everything which is high power amplification. I just talked about in gallium nitride technology. You can see some of the image on the right. As well, I will not go into the detail, but other RF development to secure the processing. And of course, ESA is following the development carefully, and the progress today is nominal. As well, we have started to do development in digital technology, which is more and more used, in particular using FPGA to have ease of programmation on board, and as well on the TX-RS synchronization, which is keeping the time correct on a radar, which is critical to any radar. And finally, I will conclude on the antenna pre-development, where we will reconstruct an antenna, which is looking like the first antenna on CryoSat, but this time we will manufacture the antenna. And we have developed pre-development where we test the stability of the material, which is a carbon reinforced plastic. And you see the development on the right with a picture of the characterization. So we will meet TRL 6 by May 22. So well in time for launch in 27. Well, this slide is making the transition to the point that altimetry is not only for Cryosphere, of course, but it's for all applications, the oceans, the waves, and more recently hydrology. And when we discuss with colleagues at ESA, we often talk about virtual constellation. So the virtual constellation is mixing all the mission altimetry to get synergy between all the missions. And while doing that, we are starting to develop a vision of an altimetry design that can be reused for multi-purpose applications. So if not all the blocks, some of the blocks can be reused for some application, and it's a block approach. And there you see three parts. One which is digital, the digital part, the RF power, which is the amplification of the signal, if you like, the antenna, and some switching matrices for going from the transmit to receive. And I will focus on one point, which is what we call IDA. So IDA is an integration of digital and RF technology in one equipment. We already started to do that for crystal, but we pursue that route to get a modular design to serve all application of in the future for altimetry. So I will move now to something new, which is source altimetry. So source altimetry, well, is it actually new? Not really, it's not, because Cyral and CryoSat were already the precursor of source altimetry. The instrument is looking at nadir, but all the basic is there. So now if you take an instrument and look on the side, you will find again all the basic things that you have on crystal. So there is strong legacy from crystal and CryoSat to go to source altimetry. And as well, you see the SWOT mission there on the left with the equipment that we built for the radar, which is called CARI, with an interferometric receiver and transmitter as well. So we will use both technology to build the future for a source altimetry mission for operational oceanography and hydrology. So we already started to look at this concept with ESA, funded by ESA. We made some pre-developments, and you see a picture on the right. I will not detail that. You see in the middle the antenna. The antenna is looking, there are three antennas. One is transmitting, that you see the TX antenna, and two are receiving. So instead of having two antennas on CryoSat, now you have three, but the principle is the same. You receive on both antennas, and you do interferometry as well as SAR focusing. So this will provide now a source instead of a single point, about 50 kilometers on each side of the nadir direction. And the transmitted power for ocean application is much bigger than on CryoSat, because now we are talking about 1.5 kilowatts. So why do we talk about source altimetry when we are in a Cryosphere meeting? Well, that's some ideas of the capability of source altimetry to be investigated further in the future world, in particular for Sentinel-3 NG application. What you see on the left is derived from the GPM data. It shows sigma naught as a function of the incidence angle in Ka band, for in blue for water and in red for the sea ice. So you see clearly that where the source altimetry is positioned, there is a clear distinction between the blue and the red. The double lines that you see are the 1 sigma departure from the middle line. So you see that there is a clear separation in sigma naught. So this is useful when we will have to process data, because we can, from the sigma naught return, distinguish between water and sea ice. So what we did very quickly for this presentation, we made a simple simulation. A colleague of mine did that. It's Frank Demester. Some of you know him. Very simple simulation where we start with a crack in the ice, about 30 centimeter freeboard, which is representative of what we get, and we simulate images using the sigma naught to delineate the crack, and you see the results there. We clearly see the elevation retrieval. You see the noise due to the speckle and SNR, and you clearly see the crack, and by estimating along the crack the freeboard, then we believe we can have a good estimation of the sea ice thickness. On the right, what you see is a potential application over land ice. You know the slope-induced mode in CryoSat. There we have it all the time, because now we look on the side, so we we will have an imaging of the slope, and within the source, depending on the slope, you will have the point of closest approach, the so-called POCA, that will move around the source. And don't forget, now we transmit 1.5 kilowatts. So already we do a good job with CryoSat transmitting only 30 watts and an antenna pattern which has some holes in it, so SNR which is not very good. Now with the source altimetry, we will get very good SNR for the POCA. So at the same time, a POCA plus a source, obviously, within the slope. So we believe that both applications for sea ice and land ice should be carefully looked at for the next generation of Sentinel-3. So as a conclusion, I think that we all can acknowledge from the presentation and previous symposium that CIRAL was really a breakthrough, and it paves the way to modern space radar altimetry. Not only for ice, it was designed for ice application at the beginning, but there has been a dramatic application for oceanography, geodesy, and hydrology. There has been a number of presentations on that. Also, CryoSat data stimulated spectacular progress in waveform processing, in particular the numerical processing. I always emphasize that to get the best of high-quality radars, we need to have long-rod processing, which is matched to the radar transfer function. So we should retract as accurately as we can, trying to mimic the physics of the measurements and the impulse response of the radar. The third bullet is that CryoSat has been launched since a long time. It's close to an end. We hope it will last longest as possible, but we should prepare very quickly the Crystal mission and send the Crystal mission. We are ready for that at technology level. All progress is going very smoothly, and we will be ready in time for Crystal launch. And the last bullet is about the source altimetry, something which has not yet been looked at, but with the SWOT data, I'm pretty sure that people will look at that, and we should anticipate as well and look at what we can extract from Sentinel-3 source altimetry for ice. Will it be for sea ice or for land ice? Okay, so thank you very much. That will conclude.
Thank you very much indeed, Laurent, for a terrific talk, taking us through this long journey, fascinating journey. I noticed that one question from Michel Samados is in the chat box, so you might want to have a quick look at that while we go straight on to the next presentation. Let me encourage you, the audience, to think of their questions for the speakers and put them in the chat box so that speakers can be preparing their answers. But in the meantime, let's press straight on to Andy Shepherd, Professor of Earth Observation at University of Leeds, well known to all of us, Director of the NERC Centre for Polar Observation and Modelling, Principal Scientific Advisor to ESA CryoSat Satellite Mission, co-leader of the ESA-NASA Ice Sheet Mass Balance into Comparison exercise. And Andy's going to give a presentation on a vision for the future path of ice altimetry. So over to you, Andy.
Thank you very much. I'm just going to share my video screen. Is that there?
Yes, it is.
Okay, thanks very much for those introductory remarks and for inviting me to give this presentation. I'm going to confess I don't have a unique vision for the future of altimetry. I'm going to present some ideas and hopefully stimulate a collective vision from the audience. That's really, I think, what Chris and Mark are after from this session. And I will rapidly reprise some of the content that you will have already seen in earlier presentations this week, because I think it's context for this study. So my co-author for this work is Sarah Flourish. You might not know who she is, but Sarah, I've listed you as a co-author because I think that this really came out of a community letter that we organized together to try and move things forwards for polar altimetry. So I want to make 3 points. One about advancing instrumentation and how we've been very successful. We've heard a lot about that this week. But the 2 main points about vision are bridging the observational gap, which we will have at some point in the future. And I think also it's important to consider the expertise gap, which I'll try and articulate towards the end of the presentation. So we prepared, Sarah and I and some others, colleagues, a community letter last year to raise concern about the imminent gap that would appear in polar altimetry. It'll happen at some stage between 2025 and 2030. And in this community letter, there's a statement of the importance of satellite altimetry for the polar regions and for climate science and other operational services. We proposed some mitigation options, collected a large number of signatures and sent it to the Commission and to the European Space Agency as being the bodies that represent us. We didn't send it to NASA because we're not American. But this is the timeline of polar altimetry, and you'll have seen this in different guises earlier in the week. We did have satellite altimetry in the 1970s and 1980s, for those of you that are old enough to remember, CSAT and GeoSat, and this is what they saw of the polar regions, the masked out area. So this is really the first generation of altimeters, gave us a sniff of the changes that were happening in southern Greenland and in the low latitude sea ice cover in winter. Then we had ERS-1, ERS-2 and ENVISAT, which had better coverage, as we know, progressing closer towards the pole, missed out some important aspects of the Antarctic ice sheet in particular, but also most of the summer sea ice cover. And that remains the case today with this orbit inclination. Then we had ISAT-1 launched, closer to the pole, CryoSat-2 launched, as we've seen, fantastic coverage and complete essentially for both poles. And ISAT-2 is now in space, providing similar coverage. And this is the evolution that we've seen in instrumentation, and we can now survey the polar regions. In the future, we hope to have Crystal. It isn't fully commissioned yet. It's a candidate mission still today. Hopefully by the end of this year, it will be a fully fledged mission with money to pay for it from the European member states. And I'm going to flash through some of the science highlights just for context. We've seen it already many times. Jonathan's wonderful DEM built from the geodetic phase data from ERS-1, an absolutely fantastic map, groundbreaking, and really paved the way for polar science, actually, for a large number of scientists, modelers, and Earth observation scientists together. Now we have complete coverage in high definition from CryoSat, and this is what people work with today. We've seen, well, we haven't seen much of this today. This is the elevation change pattern of Antarctica derived from CSAT and GeoSat from Ludwig Schroeder and others. That you can see some of the Antarctic ice sheet, actually. It's the margins of the ice sheet. We don't see any of the signal from West Antarctica, which we're all familiar with. Duncan showed a bit of it with the early ERS data, and we've seen progressively better and better quality data from ENVISAT, from ISAT-1, and from CryoSat-2, giving complete pictures of the ice sheets. This is the technology that we need to do polar science. We need an instrument with this type of capability, and thankfully that's been proposed. We have SWOT capability we just heard about, which gives us continuous measurements, and that means we can look at the small outlet glaciers in Greenland or the mountain glaciers around the planet now in a way that we didn't expect to be able to. So we need an interferometer on board as well. We need high resolution to look at sea ice flows. These are the leads detected in pseudo-LRM and CryoSat, factor of 10 difference between the number of leads detected, which improves the precision with which we can measure sea ice thickness because we depend upon the leads. We have that with CryoSat. We didn't have it with ERS, we have it with CryoSat. It provides a perfect tool for studying sea ice as well. And with a dual frequency altimeter, but people have shown that we can recover the snow layer, which I was happy to hear Valerie point out as a really essential climate variable for monitoring future climate. So we need a dual frequency altimeter. And that's what we're proposing. That's what has been proposed, Crystal as a high priority candidate mission. But there is a gap. And if Crystal doesn't get selected, then we will return to having to rely upon Sentinel-3, which provides this partial coverage, only 40% of the Arctic sea ice cover in summer and decreasing. And so we won't be able to continue to track changes in Arctic sea ice if Crystal doesn't get commissioned. It's a really sad moment for me because CryoSat was launched in 2010 and it's now 2021 and we still haven't commissioned the follow-on mission. Let's not dwell on the past, but that's the situation we're in. And I think we need to think about that in terms of the future of altimetry, not allowing this to happen again in the future. And there needs to be some system which stops things falling through the cracks. And CryoSat's follow-on has fallen through the cracks as far as Europe is concerned. So there are things we can do to bridge the gap. We could extend the lifetime of CryoSat. Tom and colleagues at ESOC are doing their very best to continue its lifetime. It's 11 years old today. Hopefully it will last 17 years to be ERS2, but it might not. We can't depend upon that. We can extend the lifetime of ISAT-2. That's in the hands of NASA, and hopefully they can do that. We could in principle advance the build for Crystal. I don't think that's possible. 2027 is the earliest possible launch, more likely 2028. I suspect most people would agree with that. We could pinch one of these altimeters. The oceanographers are greedy. They've got 7 altimeters, right, flying around in space or sitting in warehouses, but we can't do it. It would be nice to think we could, but they can't fly. The hardware isn't designed to fly in a near polar orbit, so this one isn't going to happen, unfortunately. It would be nice to think it could, but it can't. We can throw some CubeSats into space at low cost. We could set a program running right now to build and launch a low-cost, low capability but continuity altimeter system and that would bridge this gap. And I really favor exploring this option because something is better than nothing. Or we could turn back to, which is what prompted my initial question earlier today of Helen, about to a continuous survey from suborbital platforms, so IceBridge, build a European version of this. All of this needs to be explored. It's multi-agency. It's not just ESA's responsibility. It's the Commission's responsibility, NASA's responsibility, the scientific community's responsibility to explore these capabilities. And I just want to mention one other thing that I believe is really at the heart of the problem that we've got today with continuity in satellite missions, bridging what I call the expertise gap. So we all are familiar with the signals of climate change. I've showed this earlier today. We have some iconic time series of changes in climate variables that have been determined largely with satellite measurements. And if we look at, and these are historical changes, if we look at the tipping points that people have raised attention to, Tim Lenton and others, most of them are in the cryosphere. We know that the cryosphere could be a real problem for us in the future. And that's thanks to both the model predictions and the satellite observations, which told us about these two changes. This, for me, is what climate science is. It's been born out of satellite observations and numerical models that have both been developed in parallel over the past 30 years. And this is my illustration of those two things. Climate science is climate models and satellite observations, but I think there's a discontinuity. We can see that climate observations have informed numerical models. We've seen this earlier this week several times now, the improvement in Ipcc sea level predictions, thanks to knowledge of the changes that are happening in the cryosphere. So the AR5 and AR6 match the satellite observations now. These models have been improved, but we're not out of the woods because AR5 and AR6, this is not on this curve, but it's the case there, predictions underpredict ice losses from Antarctica and Greenland still. We're tracking the high-end climate warming scenarios. So these models will need to be fixed. And this is one of the concerns that I have, because this is what a lot of people think about when we talk about monitoring, building a capability to monitor the polar regions. It's commerce. This is activities towing icebergs away from oil rigs. It's shipping and maritime activities which drive a large part of the concern about the polar regions in terms of planning satellite missions. It's not climate science. Climate services are not viewed to be the most important objective for a monitoring system by the agencies which are tasked to assess the user need. Users are actually people like you and me, my kids, your kids. These people need a climate monitoring system. They don't need to be able to tow icebergs away from oil rig platforms in the Arctic as the sea ice melts there. We need to transform from having a system that's influenced by business and commerce, producing satellite capabilities of the future, to one that is influenced by the public and the stakeholders. And there's good evidence that this is the case. Unfortunately, there's a division between the skills that are called upon to build climate assessment reports and expert group reports for satellite missions. This is no fault, but I'm just raising awareness that on the current IPCC assessment report, there are no Earth observation scientists in the Cryosphere chapter. And in the Polar expert group report, which identifies priorities for next future candidate missions, there are no climate scientists in that group. There is a gap in expertise between these two bodies of science, which needs to be bridged. We need Earth observation at the table of climate science And we need climate science at the table of Earth observation. And this is my suggestion for the future, to try and change things so that we don't allow an observational gap like the one we've got in the next 5 years. And we'll be held responsible for that. I'll be held responsible for that because I've been and been on watch with CryoSat for the past 15 years, and we still don't have a successor. So we have the technology for a new system. We've demonstrated what we need. Crystal is the only candidate future mission. Please convince your member states to subscribe to the high priority candidate mission programs so that all 6 are funded, because Crystal isn't the top priority mission at the moment. I believe we should establish a task force which is bigger than the agency. And Chris, your organization is exactly the sort of body that could do this, to recommend on the gap, given all the different potential options there are. And we should build a cryo bridge capability, something airborne or low Earth orbit platform, suborbital platform, which can monitor the polar regions in the event that we have failure of satellite capabilities. And I do think we need to make more efforts to link between the Earth observation and climate science communities. So that's the end of my vision. I'm trying to be optimistic. I want to be optimistic. I want to avoid this happening in the future. Thank you.
Andy, thank you for being suitably provocative. I think that was a really great way to end the first part of this session. We do have a couple of questions. What I'm going to do is I'll hand over to Mark, and if you can take those 2 specific questions first, and then we've got some general points that we will use to structure this discussion. But I'll just respond to the point you raised about the voice of the community. I couldn't agree more. It does seem to me that, and of course, it's not just preventing a gap, it's actually trying to achieve an overlap between these missions, because the cross-calibration of the missions is always a rather important element of the analysis of the data as well. And certainly I'd be interested to explore how the ESSC might be able to help. But anyway, let me hand over to Mark. Mark, do you want to just handle those first few questions and then go into the structured discussion?
Yeah, we had, thanks to all the speakers, by the way, who've already started to trigger a number of questions in my mind, which we can touch on the discussion. But just to get a couple of technical questions out of the way, first of all, they were both posed in the frame, first of all, of Laurent's presentation, and I think these are not the kind of things we'll touch on in the general discussion later, so it's better we take them now. The first question was on behalf of Rosie Willett, whose work earlier this week has suggested that cross-poll is a great way, in particular, to isolate the return, say, between the snow and the ice interface. And so the question would be, in the evolution of altimeter instruments in the future, whether we can ever foresee that type of polarimetric information or diversity in polarization that might enable us to unlock important information about the source of the scattering. Can we give Laurent the microphone so that he can respond to that one? Yeah, Laurent, you, sorry, you, now let me try and unmute you. Yeah, I think we're both pressing it at the same time. Hang on 1 second. There, now we go.
Yeah. Well, on the principle, there is no reason why we should not be able to make polarization measurements, polarized measurements. It will be a modification to the design, of course, but and probably as well to what we call the chronogram. So we have to look at it, but there is no reason why we should not be able to do that. Now we should not forget that we are looking at nadir, right? So that the difference in polarization must be pretty small in terms of return. So has to be looked at in terms of sensitivity to polarization and radiometric accuracy.
Thank you. And while we have you, Laurent, there was a second question by Richard, not surprisingly, on the technical issue of the transmit power, which you cited, which would be required. in future instrumentation. And of course, this leads to the conclusion that you probably need a klystron. We all know of some of the technical challenges in developing klystrons, and so is that an issue in your view, and are we on that trajectory?
No, the klystron is not, because the klystron that we contemplate is coming from CPI, and it's coming from the legacy of SWOT in K-band. And we were thinking about using that klystron for the scheme mission. And what has to be looked at is the power supply of the klystron, and we already started some pre-development with ESA on this power supply. So it's not really a concern, has to be looked at for the power supply, but the EIK itself is already flying on SWOT. Well, will fly on SWOT.
Thank you very much, Laurent. I think then we should turn our attention, if Matteo can give me the ability to share the slide that we have to trigger the questions and the discussion. For this discussion session, we decided to focus on the cryosphere alone. Others who discussed other thematic elements in terms of the application of CryoSat would have liked that we didn't do disservice to them, but it was impossible to include all application domains in this discussion. We only have a very short amount of time available, and so we're focusing on, in particular, the polar cryosphere and the cryosphere in general. Of course, and this raised some of the issues in terms of the fact that we need to develop a successor to CryoSat. CryoSat was selfishly designed to address the polar cryosphere, and of course, we've learned of some of the very specific attributes of high inclination altimetry that's made CryoSat the mission that it is today. And so we'd like, first of all, to try and collect together some of the thoughts that have been triggered by the keynote speakers. And we've ordered those points in the slides, which I'm just trying to share as we speak. We'll see if you're able to see this on the screen. So, are you able to see my my screen now?
I can only see half of it. Yeah, now we can see your slide sorter as well.
Okay. So I'll just flash this slide with the seed questions up first of all, and maybe you can all take a photograph of this and retain it for reference as we go on, because I think
you might be having your double screen problem. We can see your slide sorter as well. We can just about read the main one.
Oh, there we go. There we go. You see it okay now?
Yeah, that's fine.
Yeah, please take a photograph of this now with your mobile phone so that you can retain these seed questions in your mind, because I'm going to have to take notes during the session right now. So everybody take a photograph of this before I no longer project it. And I'm going to pose the first question to Valerie, because we've learned from her talk, for instance, that snow has got a much more important profile in AR6, for instance. And so I'd like to pose the question to Valerie from her understanding of the content of AR6. What profile does snow take? Obviously, CryoSat has been developed to capture somewhat this snow theme, for instance. We realize that snow and snow water availability is going to be of particular societal importance in the future with climate change. And also it raises questions not only about dual frequency altimetry, but our ability to measure the smaller glaciers in high mountain regions and the snow cover in high mountain regions. And so maybe you have an answer about the relative importance of snow in AR6.
So what I wanted to flag is that in the AR6 Working Group 1 report, we have the chance to have a number of scientists involved in Earth observations as lead authors. For instance, in the chapter on observations, we have Sebastian Gerland, who has been involved in CryoSat for sea ice data, or in the chapter on the ocean and cryosphere and sea level, we have the chance of having as one of the lead authors, Sophie Nowicki, who has early on been involved in also the use of CryoSat data. And I wanted to flag that regarding snow, there are a couple of issues. One issue is the availability of long-term homogeneous observations, which is important for one of the essential variables, as snow cover plays a key role in surface albedo feedbacks, for instance. And the second dimension is the availability of long-term records, multiple decades, where relevant for risk management and adaptation. So at very fine scales regarding the provision of climate information that is relevant for end user needs. And that's really a strong dimension of the AR6 Working Group 1 report on not what we do ourselves within an Ipcc report, but what is emerging worldwide, which is the co-design with end users and the distillation of user-relevant, context-relevant climate information. And I think that part and taking into account the user needs regarding snow monitoring could be a core part of what could be considered in terms of observational strategies.
Now, this feeds back into the question, of course, what are some of the principal scientific challenges remaining for altimetry of the cryosphere? And one of the points that I've picked up on throughout the discussions during the week are, for instance, the importance of characterizing the freshwater balance at the high latitudes, particularly in the Arctic, for example. We know very little about solid precipitation and how to constrain the freshwater, that element of the freshwater balance. And so snow on sea ice is a very important parameter, but snow on sea ice is not an ECV yet as far as GCOS is concerned. And so that's a concern that Sarah Fleury has expressed, for instance, and yet it has to be a driver of what we try and achieve with crystal, for instance. So I hope that we can see some movement in that direction, for instance. Okay, we've had a variety of other points that have been raised about the important challenges throughout the course of the week. Are there any other points that people want to make or stress in relation to what Valerie's discussed? Yeah, it's difficult to entertain a discussion this way, isn't it, Chris?
There is, Sinead has said regarding increasing the inclination of future oceanography mission in the perspective of making a truly global assessment of sea level rise, closing the sea level budget, we must measure sea level change in the polar oceans. Been shown this week already, sea level is changing in the Arctic. With the ongoing loss of ice cover, we expect future significant change within the Arctic Ocean. Can we understand if the oceanography community are likewise interested in monitoring this? And I should just add a pet bugbear about carbon dioxide release or absorption in the polar ocean as well. It seems to be an area with a big question mark hanging over it in terms of the carbon cycle.
Yeah, I think that the point that Sinead has made is welcome, although it's principal element of any altimeter mission, of course, that we have to measure the sea surface in the polar oceans in order to be able to retrieve sea ice freeborn thickness. And so I think it's well acknowledged that any mission would have to do that as a byproduct of its measurements.
Jerome is suggesting that we open the mics to all. I think that might be the way to chaos. But what we could do is encourage people who'd like us to open their mic to just put a Q or an exclamation mark in the chat message, and then we'll try and unplug them. And they get a mug, apparently. But carry on, Mark, please.
No, but in terms of some of the challenges that you raised, I noticed on your slide you had high mountains characterizing high mountain permafrost, glacier ice, lake ice, river ice. We've covered snow depth on sea ice. You talked about mechanistic understanding of the observed changes and trends, in particular in Antarctic sea ice. That's something that's confounded us so far, is the ability to measure Antarctic sea ice with the same degree of accuracy. Andy, do you want to inject anything into the discussion there about how we should be going about tackling particularly the Antarctic sea ice cover in the future, because it's been, you could say, neglected somewhat because of the primary interest in the Arctic sea ice cover today. Yeah, Andy? Yeah.
Need to unmute. Yeah.
Just waiting for the unmute to be implemented.
Yes, I think there are a couple of important areas related to climate projections. One is tipping points, and one of the key observables that we've had at some stage in the past is the capability to monitor ice sheet grounding lines. And we've kind of lost that because you need tandem coverage, you need repeat coverage at one day or something like that, and we don't have that capability now, and it would be a very strong early warning signal. And so that's not something that satellite altimetry can deliver, but synthetic aperture radar imagery can do that. Snow on sea ice is actually it's an interesting one, because Valerie commented that that this was a recommendation from the Ipcc, but it actually is already being done. And this is my case in point. We already have retrievals for snow on sea ice, and a 6-year report recommending that we develop them isn't going to help us nudge the space agencies at the right pace in order to launch a mission with that capability. And that's where I think, I'm not trying to be provocative, as Chris said. I was trying to highlight the issue that there is this gap in expertise, and I know and love Sophie, and I have done for a long time, but she's not an Earth observation expert. She's an ice sheet modeler, and she would be proud to admit to being that. There are 15 co-authors in the Cryosphere chapter, and I think it's important that we address it in the future.
So in actual fact, one of the principal challenges for altimetry of the cryosphere is to make sure we do a better job of engaging the modeling community and vice versa, to make sure that people from the modeling community are being engaged by our scientific community to ensure that they're being brought progressively on board. Angelica, yeah, I give you the request to be unmuted.
Yeah, I think this is very important, in particular because a lot of inverse modeling approaches are coming up. So in that way, it is similar to what data assimilation is doing for sea ice models and so on. It is just a different technique, but there are so many opportunities coming up for inverse modeling. I think it is key to have an increased exchange between the modeler and the remote sensing people.
Yes, Valerie?
Yes, what I wanted to stress is the fact that in a way you cannot expect Ipcc to do what is not its mandate. And so the point is that identifying future research directions or being prescriptive on research path is not part of our mandate. In each chapter, when assessing the state of knowledge, of course, there's an assessment of advances and gaps. It's part of the process. There's a strong emphasis on observational limits and gaps, as I've tried to share. And the design of the AR6 Working Group 1 report was to facilitate the integration of multiple lines of evidence. And this was also highlighted by Angelica and many others. Constraining models using observations, for instance, is really an emerging field. And identifying the observational data that are most critical for that is, I think, part of the challenge for future Earth observation strategies. It also includes the use of historical information, the use of paleoclimate evidence as well. And that was really the intent that we had to support having a holistic approach, which is not always taking place in the research community per se. And that was also a limit into the possibilities of an assessment, trying to combine as much as possible all available lines of evidence. And another point is that there could be opportunities, if you wish, at the end of the AR6 cycle to reflect across the various reports that we have and to bring together the scientists who have been involved in doing that with Earth observation scientists in an expert meeting or workshop, so that you could also build on multiple perspectives on the state of knowledge, if you think that there is value in that.
Can I interject there? Mark, this is really a question for you. In thinking back to the early days of both ocean and ice altimetry, there were various absolutely crucial workshops, which those of us that were around at the time remember. Out back, there was a wonderful 1 month long summer school that CNES and ESA sponsored in Graz in 1982, where 40 early career researchers, many of whom are still around, laid the foundations for TOPEX Poseidon and the ocean altimetry that's subsequently come. And there was a section on polar altimetry at the time. There were other key workshops where communities were brought together. Is this something that ESA still is capable of funding? And is this something that we could work with the ESSC to frame and manage and get in place?
I think it's a very valuable recommendation that we try and achieve that kind of thing. I think the problem that we're wrestling with, and this pertains to the question that we'll come to shortly, is the fact that as we move into this from the research to the operational domain in terms of justifying altimeters, we become somewhat disconnected from the very close connection that we have with the research community. And the definition of user, as far as, say, Copernicus is concerned, is somewhat different. And so we do need to find a framework in which we can source quote-unquote user needs, which include the needs of the scientific and the research community in a relatively broader sense. And it would be much advantageous should an external independent organization like ESSC take the responsibility for engaging that kind of user workshop, because it's less ESA involved in the solicitation and the collection of the user needs in that respect.
Listen, there's I should say to all the participants, we had originally hoped that we would be able to use Slido for this section, but for one reason or another, we're not able to. And I can see people in the chat box saying, you know, can we raise a hand? By all means, raise a hand, put an exclamation mark or a Q in the chat box, and we will hand you the microphone, because we really want this to be a community discussion, you know, not just a discussion between Mark, myself and our four speakers. This is open. This is your opportunity to start to pitch in to this important area of what direction should we go in, what direction do you want this to go in. So just let me relate Jerome's point on this one before. I think we should probably move to the second question, Chris, so that we can focus the discussion again. Notably, Jerome's pointed out that we did have an Earth observation for polar meeting towards the end of last year. And there's going to be a report coming out, published from that meeting, which should consolidate many of the recommendations from that meeting. And so that already provides the first stepping stone, I would say. And through the analysis of that, we can perhaps craft a way forwards for such a workshop in future, Chris. Okay, well, unless there are further questions, I've actually got one question for Angelica, which may seg on to the next issue, and that is, to what extent, I was very interested in your cross-section of the ice sheet and the flows. And I seem to recall that one of the results after the International Polar Year was the discovery that there was a great deal of disturbance at the bottom of at the base of the ice sheet, where water was being frozen back on, where stuff was being rolled over, and the horizon were being rolled over and disturbed, and that this surely must have a great impact on the ice dynamics. And so, you know, first of all, is that true? I suspect it is, but it'd be good to hear about it. And secondly, really moving to the next question, do we need to go beyond altimetry that just looks at the surface? Do we need to start to try and develop systems that penetrate through the ice, giving temperature profiles, water content, layers, and so on? Angelica, what's your thought on this?
So first of all, the question of do we freeze on a lot of material? I actually don't think that we freeze on a lot of material. So maybe you remember these blobs that you have seen in the radar altimetry. So this is probably more a folding issue.
Yeah.
So due to the different ice dynamics. That said, part of the sliding process, the regulation is on a micro level, a melt freeze on process. So it contributes a bit, but not these massive structures. That's probably not the issue. Do we need other missions? I think we heavily need to investigate more into understanding sliding better. And there have been a couple of papers out in the last 2 years showing how much this is limiting our capabilities in improving the uncertainties of projections. In terms of what type of missions do we need, I think there are a couple of critical things. One, we need missions that go beyond 80 degrees north or south. This is crucial. I think actually, if you want to understand more of the interior structure of the ice sheet, then indeed an L-band mission is crucial. I mean, there is this ROSE-L campaign mission coming up, but in that respect, you would rather also want to go more into tomographic SAR. However, having said this, we probably don't know how deep we would penetrate, and it may be different in different areas of the ice sheet. Greenland completely different than Antarctica, but for Greenland, I think such a mission would be great. What might also be very important is to have a continuous capability in terms of doing interferometry with kind of, if you choose the way you set up the orbits, that you could have repeat passes that are in a campaign perspective able to retrieve more coverage over shorter periods of time, that would be also very useful. Because in particular in summertime, you are often lost with having a good coverage or coverage in terms of what you can retrieve. And this would really be helpful.
And in terms of complementary knowledge, how important would be a kind of super bed map, a much better understanding of the base topography, he said provocatively.
Yeah, a super bed mapper is very important. I have just been also in another meeting dealing with exascale readiness of ice sheet models. People want us to be able to compute on 50,000 to 100,000 of processors in parallel. All fine, but if my topography is based on flight campaigns with a spacing of 20 kilometers, what's the point in going beyond 150 meters resolution? So for sure, we need a super bed mapper. Yeah, I can fully agree.
And I mean, with the next topic is what core innovations are required to make Cryosphere altimetry relevant in the next decades, and I'd like to open that up to you know, I remember years ago we started measuring sea surface temperature with enormous precision and accuracy, but we didn't know the temperature of the boundary layer, so actually working out the fluxes was more difficult. You needed both to be able to do the job properly. And so there is a potential that we refine altimetry to the point where the limitation is actually in the supporting data sets. So the question should be, what are the core innovations required to make Cryosphere altimetry relevant in the next decades, including the supporting data sets from other missions that or other types of instrument? So I throw that open. And I guess, I mean, Laurent might very well kick things off, but maybe other people would want to join in as well.
I give you the mic if you want to start, Laurent. I've noted from your presentation, of course, we've seen the progression to greater precision instruments in the range direction, as well as higher spatial resolution along track and across along track and across track dimensions. And we've seen how we're making an evolution towards dual frequency instrumentation to be able to zoom in on the different returns from the top and the bottom of the snow. So maybe you want to add something in response to Chris's question.
I'm not sure I'm the best person to respond to the question about supporting data set and corrections. I don't know, not follow all the science presentation. I don't know, for instance, if there is any problem with tropospheric corrections when it comes to the Cryosphere. I've not seen anything supporting the fact that we need a radiometer for the ice. Maybe there is good point for that, but I don't know. Maybe, I lose a little bit track since a few years on what's going on retracking, but I have the feeling that retracking really is a key issue, in particular over sea ice, where there are assumptions that the surface is flat while it is not flat. It is a rough surface, including sea ice. So I would think that there is effort as been done in the past for doing numerical retracting over the ocean. How to include the roughness into retrieval over sea ice in KU and K-band. I think this is really a key issue for the future. I don't know what you're feeling. I come the question to the science.
That's a good one. We've also seen other points made by Angelica in her presentation about the need to be able to sample or to better sample tidally driven processes, and I'm wondering whether we've explored all of the space that we need to explore in terms of configuration of orbits or combinations of satellites in different orbits in order to address those points. Obviously, we've been limited with the types of orbits we've had with altimetry in the past. Be able to sample tidal processes was something that I understood that you were pointing towards, Angelica. Is that true? So daily. Yeah. Unmuted now.
Okay. I think what's important is, I mean, it's not the tidal forcing that is driving the ice sheet retreat. It is the interaction of this system with the subglacial hydrology. But what we need to know is, if we look at grounding line migration and grounding line retreat, we need to have a very dense coverage of interferometry in order really to constrain what is a tidal signal and what is a retreat. I mean, that's well known since the 90s or so, but still we are having a limited capability of that. And indeed, in that case, it would be very useful to have the altimetry data in a close proximity of a coverage of a radar mission. May it be a C-band, an X-band, or an L-band mission. But that would be useful. Or also a laser mission. I mean, depends on what type of altimeter you want to combine with which one. Yeah.
Mark, you're muted.
I don't know if Sinead wanted to jump in at that point.
Yes.
What I could say, first of all, before you do, is, of course, we have the Roselle mission that's being planned within the Copernicus expansion scope. And we also have NISAR in the meantime, which will sample at a high latitude over Antarctica. And so we do have the opportunity to preview L-band interferometric SAR before Roselle comes along. And that will give you the type of coverage that you were yearning for, certainly in the central part of Antarctica. But Sinead, you wanted to complement with your point? I unmute you.
Thanks so much, Mark, and thank you for this really helpful conversation and discussion. I think this is a really needed discussion. Just a comment regarding cover in particular in terms of the needs going in the future. The thing that we can say, particularly in regards to Arctic sea ice, is that it is thinning and drifting faster. So we're seeing a shift from the old times, the past glory days of sea ice, where we had thick multi-year ice cover, consolidated ice pack, to a more seasonal sea ice cover. And of course, this is already the case for most of the sea ice in the Southern Ocean. And because of this, we need to really focus on high resolution altimetry measurements. You know, spacing between ice flows where your lead frequency is increasing means that your footprint has to be, you know, narrow. And the capability we require also includes the vertical precision so that we can measure the thinnest sea ice. So because of this transition due to climate change in the ice cover, the technology that we really need from altimetry in the future is high resolution. And I would just say, in terms of the chat, I think Steve just mentioned putting laser and radar altimeters on the same platform. I do personally believe that that is whether they need to be on the same platform or in coordinated orbits like we have now with cryo to ice to some extent, that will provide a really important future capability, in particular for measuring sea ice, in addition to all of the other parameters about sea ice that we're interested in, like melt ponds and flow size geometry and all of that. So thanks.
Thanks, Sinead. I've just, Jerome has raised a question that was in the back of my mind as well. He's saying, what about microsat constellation? He said like SMASH, but there are so many of these microsat constellations being launched at present. And I suppose the question really is for, I mean, you know, Mark and Laurent and others who know these things, you know, what is the shortest turnaround time that a what you might call relatively quick and dirty altimeter mission might be put together with the potential CryoSat crystal gap in mind? Forgetting the programmatics for the moment, obviously that's another hurdle as well. But if we had a big lump of money tomorrow, how quickly could we turn around something that would provide some useful data?
We've had a test of this, right? I mean, CryoSat 2, 3.5 years. There's your answer.
Okay, but that, yeah, all right. I guess that's a fair enough answer. Right, so that it takes us straight to the programmatics, because the programmatics to make that happen are a little troublesome, I guess. And is there nothing that can be gained from a series of smaller altimeters? I mean, you could fly a constellation that would give you better spatial temporal coverage. So is that a direction, you know, looking at this question, what core innovations are required? And we're thinking, of course, in the long-term future, we could think ahead to 2040, 2060, because those are the timescales that we've been talking about since we kicked this whole process off with ERS1, ERS2. You know, what might we envisage as the way that we use altimeters in the longer term?
So the platform I showed was a startup in the US called Busek, and they had a 6U CubeSat altimeter. They have a design for that, and I think that would be obviously very low cost. It would be nice to think somebody could invest in that, but Europe can't. Unfortunately, we need a European company. I believe there's a Spanish company that has a CubeSat altimeter as well. I'm not the biggest fan of throwing confetti into space, I have to say, but needs must, and if there is a system that can bridge the gap, then that would be great. But back to the observational capability, I think I agree with Sinead that the sea ice flows are actually one of our biggest challenges, and to have an imaging capability at the same time as altimetry would be fantastic. And we've moved away from multi-sensor platforms for obvious reasons. It may not be the case that they have to be on the same platform, but they could be, for instance, in a tandem orbit or something like that. So having contemporaneous SAR imagery with an altimeter for sea ice flows would actually be a game changer, I think. Interesting.
All right. There I can respond, Andy, because we have been looking throughout the PEC 3 process, which was the whole expert group of the Commission, at the architectural aspects that would enable you to combine many of the measurements within the constellation of Copernicus satellites. And so the idea is to try to optimize the architecture so that we can get the closest possible collaboration, if you like, between the different measurements over the Arctic and over the polar regions in general. And if we can achieve by architectural design those kind of collocated measurements in the future, then that's certainly one big advantage of a mission like Crystal flying as part of an overall Copernicus architecture. And you wouldn't get that advantage were it not for being able to design a mission which is complementary to the other ones that we know fly in the same time frame.
Mark, shall we move on? I'm just noting we've got about 10 minutes of discussion yet, and then 5 minutes to try and pull these threads together.
Next one.
I think there is a really this question about the transition from research to operations, because that's clearly been a stumbling block that we're currently confronted with. So the questions we'd put up were what is the programmatic home for altimetry, and how might we manage the situation that we're in, but more generally, what is the programmatic home for altimetry? Andy raised this point that we've got different communities managing different things. They don't talk to each other necessarily very well. So how might we try and deal with that gap?
Yeah, Valerie.
And Richard has put an exclamation mark up as well.
There is something I had in mind but have not yet expressed. It is the following. When you have a longer and longer time series, and you are able to address and inhomogeneities and reconcile successive observational data sets, it also opens the possibility to develop products that provide not only the observational data, but also the detection for unusual events. And what is also developing worldwide is the approach of fast attribution, so that you can link a driver or a process to a signal that is detected as unusual. I have in mind, for instance, the World Weather Attribution Initiative that within a few weeks sometimes can perform attribution studies for unusual events. And I was thinking that the design of monitoring projects may also consider this as a service for society that could be very relevant. I flagged one aspect, which was the onset of potentially irreversible behavior for some aspects of flow. That really requires further research across various communities. But for other aspects, for fast responding components, I think this could be designed closer to the monitoring system, building on existing methodologies.
Yeah, very good comment.
That's a very interesting point. Of course, one of the things that Chris has pointed to about the programmatic constraints is, of course, as altimetry is perceived to have become more and more operational, it's forced us to think about placing it in an operational framework. And the consequence of moving to Copernicus, of course, is that we have this schism growing between, if you like, the research community, who may be less regarded as the prime user of Copernicus than the people who are generating the service products and the service data sets out of the Copernicus services themselves. And so we do have to ensure that we retain a connection between the two, because of course research is at the heart of many of these services anyway. Andy, let me unmute you.
Yeah, I think it might go lost on lots of people that the Copernicus program has a set of core users, and the research community is not a core user. And it's a good question to ask about altimetry, where its home is, because right now altimetry's home is in the ocean science community. Absolutely, they provide a service that has a very, very strong connection with Copernicus user bases, and they drive. And they've driven the development of altimetry for decades now. But it is clear that the climate science community, and then of course society, needs the observations in the polar regions, and something has to be done in order to raise the profile of the climate science community within the Copernicus services. And so just as I pointed the finger at Ipcc, I point the finger at the Polar Expert Group as well. They should be engaging with Ipcc. The Commission should be engaging with Ipcc to ask which observations are of critical need, not just for improving projections of the future, but hopefully, right, the Cryosphere has been one of the fastest areas of the climate system to respond to climate change in a negative way. Hopefully, it will be the first area to respond in a positive way, and we want to be able to track that response and be sure that we're on the right pathway. So we need these observations to support not just targets for CO2 emissions and their impacts on the climate system, but also the communities that depend upon those measurements in real time. So I think I would really welcome Ipcc or some international body taking an interest in which satellite missions are commissioned in the future.
Can I just interject here, Andy? It does seem to me there's an opportunity here. If we take, for example, the role that I don't know if you know him, Tim Reeder played when he was in the Environment Agency and responsible for the Thames Estuary 2100 project, which he led and which is designed to protect London against flooding from sea level rise and storm surges. He understood that he needed the data from the climate science community and also needed monitoring information to help them make their decisions and indeed run things like the Thames Barrier and so on. You know, you need operational data. So there are communities out there who, even if they don't know it, do actually need data about going through. You mentioned the many tipping points in the cryosphere, and so I think there is an issue here that we need to reflect on. How do we connect ourselves to those people who don't even necessarily recognize that they're our customers, but who would be recognized as customers by Copernicus and who would then draw us in to the whole process of defining the future of the Copernicus services? So Angelica has a response to that.
This is exactly what I just wrote in the chat. I mean, it is really like we plan as we are not expecting an instability to happen. Yeah. And if we would not know how fast former instabilities happened. So this is the case. So these people need local sea level change. What would they need for local sea level change? It's a mass loss product from whatever kind of sensor, but a mass loss product that you can use to compute the fingerprinting. Yeah, you need to compute the fingerprinting to give this information to coastal planners, and then you need to do it quickly. This, at the end, it is a risk assessment. If the society decides they need it, they should go for filling the gap. If the society thinks we can deal with it, even on short notice, then fine. But it is something that people who need this information should be made aware of, that they may get into such a gap.
And if I might add, once the tentacles begin to spread, then you find that financiers, insurance companies, all sorts of other people need this information too. For example, it's ironic that by protecting the London floodplain effectively against sea level rise until 2100 has encouraged the development of more and more billions of investment on the floodplain, which in the end we may well have to abandon, because in the end there's only so much sea level rise you can defeat. So I think there is a growing community of people out there who we need to connect with and would help us with this "where does altimetry sit" question. And I'm going to take that as one of the lessons learned from this session and reflect on how we might address it. There was a question, an exclamation mark from Richard Francis. So can we unmute Richard and see what he wanted to contribute?
Okay, can you hear me?
Yeah, there he is. Hello, Richard. Good to see you.
Okay, hi. Yeah, actually, I'm apologise for drawing a discussion which happened a while ago, because that's when I raised it, and it's moved on quite a bit from there. So sorry about that. I'm going to draw you right back to the CubeSat story, and it's just an observation that CubeSats are always launched as a piggyback on somebody else's launch. You never have a dedicated CubeSat launch unless it's a complete launcher full of CubeSats, which are all for different things. So it means you've got to go to where the launcher takes you. Now, these things also are pretty small. They don't have any substantial orbit change capability. So to get one into a high polar orbit means waiting for the next launch. It's a very, very unpopular orbit. The next one that I know of is Crystal. So if you want to get a CubeSat, your best chance is to wait for the Crystal launch and put it on there.
Thank you for that comment.
So sorry about that, but
we had an appended point, Chris, on the need for international partnerships as well. Of course, we've seen how being able to assure continuity in missions is at the root of these long time series that we've been able to develop. And of course, we've been developing and cultivating the relationship with our US colleagues as well, particularly in the frame of Sentinel-6. And there are also possibilities for collaboration in future elements of the expansion missions as well. And so I'm wondering to what extent we have to elaborate on these international partnerships to make sure we can assure these long time series of altimetric measurements in the future. I wonder if anybody wants to comment on that question.
There are some new players coming into the game. I mean, UEA, for example, has got a mission buzzing around Mars and so on now. Maybe there are opportunities with new players that we could explore. So that's something we should just note down. That I don't know where that would lead, but it might lead somewhere. Helen has noted that the US Decadal Survey has designated this elevation as a targeted observable. So whatever happens in response to the Decadal Survey obviously would be of great interest.
Yeah, and I can reinforce that we have a very active conversation with NASA through our bilateral means. We've entered into a new era of a strategic partnership there, particularly on climate-related issues, and hopefully we can explore where the possibilities are for future collaboration on missions as well in that frame. Although I was particularly triggered by some of the statements about one of the things that we should be looking at is the possibility, for instance, to put an active optical and an active RF instrument on the same platform. And it seems like that opportunity could only ever come around these days with that type of collaboration between, say, NASA and ESA, given that we focus largely on radar altimeters and NASA's focused largely on optically based measurements over the last decade. So,
well, Steve Baker suggested that, of course, the cost sharing on something like that would be essential, because we've seen with the recent E11 process that cost on these missions is becoming a constraint. And if you really want a lot of active instruments on board one of these platforms, you're going to have to pay a lot of money for it. There are a few other questions coming in. Sarah Fleury says polar orbit needs large solar panels, so not sure a CubeSat can embed large enough solar panels. Yeah, good point. Jerome is saying we need a variable gravity mission simultaneously. That makes our job even easier. But yes,
in fact, we're doing that, Chris. We've got that's why we do have a collaboration with NASA on the next generation gravity mission. So
that's true.
We have a phase A approved. We're entering into a collaborative preparatory study together with NASA so that we can couple our European ideas with what NASA's got in their decadal report for the next generation of GRACE-like capability. So gravimetry and SAR-based measurements, I believe, are very well covered. And yeah, we do need to pay attention to the complementary altimetry data stream, because Angelica's emphasized, of course, this need for the complementarity and collocated measurements. And surely it's the altimetry, particularly in the high inclination orbit, that we have to protect. So Andy, you want to add something there?
Yeah, before we end the discussion, I probably distracted you by showing the CubeSat, and everyone gets excited by CubeSats, right? We have aeroplanes, and Sinead's already mentioned this. We have a capability, an airborne capability. We just don't have a systematic airborne capability for long-range observations. And I think this is something that the agencies, at least ESA and the Commission, could work together on. The Commission could pay for the bridging activity, to flying the thing around the planet, to survey, in particular, Arctic sea ice during a gap. ESA could pay to build an airborne platform prototype of Crystal, for instance. But this needs two agencies to work together, right? This requires bilateral conversations. It probably requires scientific advice from outside the agency, both agencies, for instance, because they don't have all the competencies. And I think that that's probably the most fruitful avenue in order to solve the gap. And I would really encourage Chris, you to think about that as well.
Yeah, well, in that respect, since we've only got a couple of minutes left, I'm taking away a few things from this. I don't know how many of you know about this new agency that's been set up, USPA, but there is some hope that that may allow conversations from groups like ourselves to find traction in the Commission in ways that has been more complicated in the past. The Commission is always a little bit more difficult to deal with than perhaps the ESA interface. So what I'm taking away from this is that we would need to reflect on how best to attempt to bring these two groups together. I mean, you mentioned airplanes. I suppose drones might be an idea as well. That might be a cheap way of doing automated, pilots having to drive these, fly backwards and forwards all day long to carry out these raster scans. So what I'm going to take away with the ESSC is a lot of these messages, but the key one is to find a way to bring ESA and the EC, the modelers and the observers together in a way that will help us, first of all, ensure that we don't suffer the same gap between crystal A and crystal B, for example. But secondly, to see if there's something that could be done extra in the current potential gap. We do have a good opportunity. The ESA DG comes from a background where he understands this issue directly, so that's good. People at the top are well briefed. And I will certainly go away and figure out what our next step should be. For anybody who's listening in this group, if you want to be involved in that process, if you want to make suggestions, please send me or Mark comments. We can make sure our emails are available, and we'll get back to you in due course on what the next steps will be. I think my comment, I'm going to hand back to Mark, but I'll just say that I think we've bumped into a limitation of not meeting together, and my God, won't it be good when we can actually hold one of these discussions face to face, even with 100 people. I think we would get a little bit further than we did struggling here over the internet. But I'd just like to thank everybody for their contributions, in particular for terrific presentations. Really appreciate that. And so I'll leave Mark to finish off.
No, thank you very much to all the speakers and for everybody staying so late in the evening. It's clearly a topic that we have to continue to investigate and shall do so. We have an active open conversation with the Commission, of course, through the preparation of the development of Crystal. And as we start to prepare for the Living Planet Symposium next year, we can also foresee how best to trigger some of these continued conversations in the context of sessions at LPS next year. So for those people who want to help us to stimulate and prepare some of those sessions, let's start thinking about the content for the Living Planet Symposium in Bonn in 2022. One of those sessions, obviously, that we can foresee is a session on CryoBridge, for instance, and this entire discussion about what's required in order to bridge a gap, a potential gap between CryoSat end of life and Crystal, should that happen. Not least also building this systematic airborne capability that you've mentioned, Andy. So we within the agency, certainly keeping our ears open to the community to make sure that we prepare the right sessions at LPS next year. And of course, that particular issue is foremost in our minds, the airborne capability, Andy. So yeah, thanks very much to everybody for staying with us. Yeah, I'm sorry as well that we have to use this virtual means rather than a physical session in Taormina. I'd planned a holiday there as well, and it's a disappointment that we've not managed to make it, but we'll get back there, I'm sure. Tom is going to work to make sure that we can see his birthplace at some point in time before the end of life of CryoSat. So thanks to everybody for participating, and have a great evening, and let's return tomorrow and see the rest of the delights of CryoSat. Thanks, everybody. Chris, I'll capture the comments in the field before we.
Okay, shall we stay on, Mark, or do you want to go on to WhatsApp?
I can stay on.
Yeah, okay. Yeah. Let's let people leave first. I don't know if you managed to keep notes.
I've got lots of notes. Yeah.
Mark, I'm just checking whether you and Chris are co-hosts. So, okay, make sure that everyone is left, and then I'll leave it to you. So WebEx is not switched off, and then
okay. I think we just need 5 minutes to next steps.
Congratulations, by the way, it was very nice and well attended. I'm keeping statistics of all the sessions. This is one of the highest. And
excellent.
But again, it's we are suffering from the limitation and not having no physical meeting. I think this session could have lasted another hour easily.
There was I got the impression there was a huge latency of people who would have liked to have engaged but felt a bit constrained by the format.
It's impossible to inject a comment at the point in time where it's relevant unless you can conveniently take the floor or put your hand up, and I think that's the limitation of WebEx chat to try and trigger.
That's true.
Yeah. We're gradually working down now. There are two of me because I decided I would have belt and braces, and so I've got one screen that's got the chat box on, and the other I'm actually using for the communication.
I did the same because lesson learned from yesterday.
Yes, indeed. Mark, very quickly. I have another commitment until about 10:30 tomorrow morning. Do you want to just put together some thoughts, and then
I'll have a go at consolidating my notes and plucking out some of the main points. I think a lot of good stuff was triggered by the keynotes that will help to consolidate general points that were relevant that came out of the discussion as well. And I can try and put those things down. You wanted more of recommendations, did you, Tom, or more of summary? Is he there?
I think he may have gone.
Yeah. So it wasn't clear to me if he wanted a combination of summary, high-level summary, and recommendations.
I got the impression that he wanted some recommendations, particularly from this session. But
we've got a few really good high-level ones, like this schism that Andy raised at the end of his presentation, and which is illustrated by the fact that the polar expert group doesn't have scientists, because of course the Commission turned to quote-unquote operational service providers for their user input, and I think that's one of the problems. It's one of the challenges. Actually, I would like to say to the people who are participating, if you don't know who your Copernicus user forum representative is, then you've not tried to inject user needs into the Copernicus dimension. And everybody should get to know who their Copernicus user forum representative is at national level, or if they want to inject something at the Copernicus climate change workshops or fora, of which there are very many all over Europe. If they're not attending those and saying what they need, they'll only listen to the operational community, which is the NWP centers, the ICE monitoring centers, etc. Yeah.
Well, look, I've got a couple of things that you know what? I've got a couple of things that I think I might just discuss with you on the phone, Mark, because they're slightly sensitive, but they're very relevant. So should we shut down now? Should we shut down now and pick up a WhatsApp?
Okay, that's good. Yeah, that's good. Okie dokie. Yeah.
Cheers.
Okay, see you on the other channel. I'm not going to leave the meet. Yeah. Thank you very much, Veronica. Thank you for hosting. Matteo, thanks for the great support.
You're welcome. Have a good evening. Bye.
You too.